Hi everyone, it's Mr. Baker here. Today we're going to be looking at components of a force. So we've looked at how to draw forces, and today we're going to be looking at drawing forces again, but how we can look at the components, the bits of the resultant force in a bit more detail. So we're going to be able to describe what a resultant force is, and we're going to be looking at the motion of objects which have got resultant forces here as well. We're going to be looking at equilibrium, looking at horizontal and vertical forces, and we're going to be able to see if we think something is in equilibrium because of the forces that are on it. Right, so let's have a look at this example of a clown on a slope. Why not? So what I'd like us to do to start off with, you could maybe do this. You could draw a diagram to show what the resultant force of the car would be. What motion does this result in? So I'll just maybe pause the video, see if you can draw those forces, and then what do you think will be happening to the car? Okay, so we've got the weight here acting down, and we've got our normal force here. So if we were to draw like we did before, we could draw those two forces. So these would be the components. This would be the resultant force acting down the slope. It's the resultant force, and so that would mean because there's a resultant force on it, it must be accelerating. It'd be accelerating down the slope as we'd think. So car on a slope accelerates down the slope. Okay. Right. Have a look at this. Tallest water slide ever. So we're going to be thinking about force. So again, this is something you could do. Maybe draw what the forces on somebody going down a water slide would be. What do you think they would be? And I'd like you to think about this really. So you'd have a force arrow for their weight, so you could draw that. And then what we can do is we can think of any force as two other forces, two components. And these two forces would be at right angles to each other, and they would make up the original force. So I'd like you to think, right, so we've got force, so try and draw the components of that force. Okay, so this is what we'd be looking at. So this is my person going down a water slide, and that person would have force on them, which would be weight, just acting straight down. Okay, so this force here, this weight, would be, we can make this up from two components of this force. And these two forces would be the ones that would be holding this person onto the slide. Okay, so we'd have a force that's pulling down the slope, and we'd have a force that's pulling them into the slide. And we know that because they're not flying off the slide, they're not jumping up out of the slide, they're not moving up the slide as well. So we'd have a parallel component to the slope. So this slope here, this slide as it is, we'd have this parallel force here, and we'd have the perpendicular force. So these two arrows here, these two bits of this force, they'd be called the components, and they would make up the resultant. So if we were to draw them all out, so this is our weight, this is our parallel component to the slope, and this is our perpendicular, so it's at 90 degrees to the slope, and these are our two components that would make up our resultant force here, which would be the weight. Okay, so that's what we're really thinking about. So it's kind of like doing what we've done before, but in the opposite way around. So what we've done before is we've taken two forces and we've made a resultant. What we're doing really here now is we're taking one force resultant and we're seeing what the components of the force would be. So the perpendicular component shows the size, the magnitude of the weight that will be acting normal to the slope. So normal again is just another word that means right angles at 90 degrees. And then the parallel component shows the size, the magnitude of the weight that will be acting down the slope. Okay, so we've got this weight that's pulling them down, And we could break that up into two components, one that would be a force into the slope and one that would be a force down the slope. So what effect would they have on that person? Well, we saw what effect they had on that person. It would be them accelerating down that slide, wouldn't it? So when we've got a force, one of the things that a force can do is it can accelerate the object. Right, how about equilibrium then? So you've probably heard this word before. In terms of physics, basically we have a specific meaning for it, and it's this. So if an object is at rest, the forces, we say, are in equilibrium. So at rest means stationary, not moving. So if something's not moving, then we can say that the forces are in equilibrium. And for an object to be in equilibrium, we need these two things. The resultant force on the object has got to be 0, and the forces acting on the object have no overall turning effect. So it's not twisting it around, it's not moving it around like a handle or something like that. So the forces aren't trying to twist around, they haven't got no overall turning effect. So, kind of obviously, but how do we know if an object is in equilibrium then? So if we have parallel forces, the sum of them equals 0. So when you add up the forces on something, then they will add up to 0 in parallel. And if they're not in parallel, if the size and the direction of the forces acting on an object are exactly balanced, the resultant force is 0. Okay, so it's probably worth just having a read through that, making sure you have got that, you understand what that means in your head. Maybe pause the video, just think it through, and then we'll move on. So taking these things then that we've just said, I want you to think about what, if this object is in equilibrium or not, and then if it's not, what is the motion? Or even if it is, what is the motion? So we've got another object on a slope here. It's got some weight. So we take our two components, the parallel force to the slope and the perpendicular force to the slope, and then we can get rid of that force, that weight there, because that is just what these two, so these two forces were making up the weight. This object isn't flying through and falling down through the slope, so it's got this normal contact reaction force there. So now we're saying we've got these three forces on it. Okay, so is the object in equilibrium or not? So let's have a look. So if I was just to take just the three forces, I can see all this force and this force, they look like they are exactly the same size, they balance each other out. So I'm left with just this one force, and if I'm left with one force, then it's not going to be in equilibrium. It's got to be accelerating, and it's going to be accelerating down the slope. Okay, so is there a way that this object could be in equilibrium on this slope? Have a think about what other force there might be acting on something on a slope, and what would that mean? Okay, maybe try and draw it, maybe pause the video, and then we'll go through it. So this is our diagram of something that's in equilibrium. So we'd have the weight that's acting down, the two components of the weight, the one perpendicular and the one parallel, like we said before. So this one here is the force that's being made up of these two. So we've got then the normal, which is balancing out the perpendicular force, and we've got the parallel force, which is a component of the weight down the slope. If we had some friction, then the friction would balance that force out, and that object would be in equilibrium. Okay. Right, so we've looked at the components of a force today. We've described what a resultant force is, and if the resultant force is 0, then the object is in equilibrium, and we've looked at a few other things as well. And that's it for now. It's Mr. Baker signing out for now, and I'll see you next time. Thanks very much.